back and forth my laptop. Multiple sequence alignment. What's the definition of it? Well, that's quite cumbersome, you would say. You've learned how to align two sequences in various ways, and as soon as you have 3 or more sequences, we talk about multiple alignment. And from multiple alignments, you see one with a number of sequences, protein sequences, orthologous protein sequences from various organisms. You see that you can learn from it because all what you see in coloring and so on, and the stuff on top, secondary structure, is maybe learned from this multiple alignment. So it's a rich source of information, and indeed I think most methods, applications in bioinformatics make use of a multiple sequence alignment as an input. We've talked, for example, about PsyBlast. What is that doing? It's doing a homology search iteratively, and on the way it all the time builds a multiple alignment, extracts a profile from that, so it uses that information as well. So, to remind you a little bit on what types of homology there are, homologs, of course, having a common ancestor. It's a binary criterion. You have a common ancestor or not, so you're homologous with another is a type of homology relationship, and this happens after speciation events. So these are 2 corresponding genes, you might say, in 2 organisms that have descended from the same common ancestor. Paralog is a copy within a genome, and that therefore is necessarily also a homology relationship with the other gene on the genome, and therefore with any corresponding gene in another organism. Xenologues are, that is a bit more difficult. These are bits of sequence, or sometimes even complete genes, that are going to be exchanged, not through a vertical line, not through lineages, but in a horizontal way. And this happens most of all, of course, within bacteria. Yeah? The idea is you stand in an elevator, you go 10 floors up, and you've taken some genome information from your neighbor in that elevator. Bacteria do this, more or less. We don't, I hope. Okay, so how does this all come into play? Speciation events and duplication events, and I think I showed you this slide before. And so here you see from an early global gene, first there was a gene duplication, so alpha and beta are orthologous genes. Are paralogous genes. This is a gene duplication within a genome, and then you see that you get a speciation event here that happens at the same time, this one and that one, and then you can talk about orthologous genes. So frog alpha, chick alpha, mouse alpha are orthologous genes, and the same holds for the beta genes. Yeah, so you can, with a bit of luck, do this kind of reasoning if you have a multiple alignment available. So, are alignments useful? Well, they are. You see that nice programs are being made with colorings. You don't need to color those in yourself. Here is probably some kind of you would say, a conservation measurement, because you see that what is red is conserved here. And you see that highlight bars are there where there is color, so that corresponds. So what can you do with a multiple alignment? Well, first of all, you can look at conserved patterns. What is important is conserved throughout evolution. So you can do evolution analysis. We'll do at least 1 lecture, if not 1.5 or 2 lectures on phylogeny, where trees are the normal way to express, to show evolutionary relationships, and input there as well is normally a multiple alignment. What you can do from it is structure prediction. Secondary structure prediction, predicting the alpha helices and the beta strands. This will be a big thing in the course structural bioinformatics. You'll hear all about it there. But these are structural elements that you can, in the meantime, predict rather well using a multiple sequence alignment. Motifs. You see letters that are conserved, what spacing, what kind of things are very important functionally very often. And therefore also, not only can you do structure prediction, but function prediction is also some of the things you can attempt to do. So, multiple alignments is ubiquitous, you might say. Is it used? Yes, they are used. Here is one of those papers. The Blast paper is maybe the most widely cited paper, certainly when it comes to a computational method on this planet. But a good second in the meantime. For years, this was the first cited paper in our area. that crystal W has been abolished, so therefore it doesn't accumulate any more references anymore, and the PsyBlast paper there is still accumulating that on a daily basis. So is this a lot? I can tell you it's a lot. By showing you the two most important journals. So basically, how do you calculate an impact factor of a journal? So how successful, you might say, is a journal? What they do for this? They take last year and the year before that, count all citations of papers that have been published, that were cited in that year, and that is the citation index for the year X. That is one per input for the citation, for the impact factor, and then the other one is just all the papers. So basically, it's the average citation, number of citations per paper over the 3 last years. So it's a very simple measure. So where are the two most successful journals on average then? Nature and Science. They're at 40 and 37. Yeah. So that's what you expect. A very good paper published in, on average, in the best journals there are is 40 times. So now look up. Are you impressed? You should be. Yeah? Even if you divide that by, this is about 2 years. I told you the story about Des Higgins. That's the second paper, Crystal W. University manager stormed into his office and said, what did you do to us? Because there's one piece of information I didn't show you, I think. That's not on here. Why is that not on here? Comes. The Crystal W paper is from 1994. In 2014, that paper was 20 years old. And university rankings, everybody's eagerly every year, all those universities like, oh, how are we doing? How are we doing? One place, fantastic, we're so good, we're so much better than last year. They use a 20-year window. So, unfortunately for University College Dublin, the Crystal W paper dropped out of the system, and that brought them down by nearly 60 places on one of those rankings. Single author. Hey, that's power, right? Okay, but they weren't happy and they didn't understand the system, so they were angry with Des Higgins, and he had to explain them that they should be happy about it instead of sad. And he's trying to. Other papers that are well cited, and he's even doing that. So, anyway, that's about usage of multiple sequence alignment. So, what is important to realize that sequences, certainly when they're important and they fulfill a function in an organism, tend to be conserved. That's also that they hold evolutionary information and memory of that about mutation rates and all kinds of things. So you can look at those sequences and learn from it. That's the basic point. And of course, you hope by conservation, by observing conservation, that you can pinpoint domains or sequence regions that are critical, important for its functioning. And of course, we have to realize as well also that sequences can of course be mutated and rearranged, and all kinds of tricks. Certainly at the protein level, you get permutations, you get olefinic circularization motifs. You have ABC, and then other protein has BCA. All kinds of things can happen, and that makes it of course more difficult to use homology as a signal to learn all kinds of patterns. But if it works, you can color it and be happy. And by the way, here is another incentive perhaps for you to start using multiple sequence alignment. Because if you do, you're a bit lucky, do a bit of work around it, I must say, you might have your name attached to a motif that you found through multiple sequence alignment. And this is the Walker motif, which is the functional motif of an ATP synthase, the catalytic region. And you see very often when it's functionally important, it tends to be conserved. Yeah. And how do you measure conservation? Of course, when you can measure this using a wide set of sequences, if you only include apes, monkeys, and human, okay, if you then get conservation, that's maybe not such a big deal. But if you would have a bacterial sequence with the same conservation, hey, you're really in business, of course. Then you have something important. Yeah. So I'm going to explain this lecture in the next. What kind of issues happen? What kind of algorithmic things you can do? What tricks people thought about? Because to make a multiple sequence alignment, you try it by hand, you'll see it's really a combinatorial problem, and it's leading to a combinatorial explosion. So most of this lecture is about these things, and then the basic algorithm that is used worldwide still to do it. Okay, but still, these are questions you want to ask. How do you get a multiple alignment? Well, nowadays you have a wide choice of available technology over the internet. No problem in that sense. But, Do you want to wait 2 weeks, have a good alignment, or do you want a quick thing and have a look immediately? Or do you want some kind of compromise, a pretty good alignment that is not all that slow, things like that. Whatever do you want to achieve is something you need to think about when you choose, when you need to select technology to make a multiple sequence alignment. Okay, so what do we know? How to align sequences pairwise, right? So this is how it went again. You have a sequence here and there. You've just finished. You should tell me how this works, but we won't. And you know now that an optimal alignment corresponds to a given path through that matrix, and depending on your type of alignment, global, semi-global, local, you find your cell, you do a traceback, and so on. So we know quite well how to align two sequences. But here we need to align 3 or more sequences. So how do we do that? Well, basically, there are 2 classes. There is exhaustive approaches, like look into all possibilities. In fact, that's what you do when you align sequences pairwise. You look for virtually all possibilities by dynamic programming. Could we play this trick for 3 or more sequences? Think about it for a moment and I'll show you. So basically you're going to look at all possible alignments between many sequences, potentially. And you look for that optimal solution by dynamic programming, and I think and I should have put 20 varies there, it's quite slow, but I'll show you why that is. And then of course, because of that problem, people smarten up, so we can't do it. We need to use some rule of thumb and a heuristic algorithm that takes basically shortcuts. And what you do fundamentally when you use a heuristic, you have your search space, and the search space is absolutely vast when we talk about multiple sequence alignment. And what you try and do is try to quickly say, okay, don't look here, don't look there. You make your search space smaller, and by doing so, hope that you find your best thing in the corner you look into. And if that is not true, your heuristic will not work very well. But heuristic is defined as something that makes it likely that where you select to look, that there is a high likelihood that the right answer or the optimal answer or the answer you would like is to be found there. Yeah. So, and it's much faster, of course, that's the main driver for this. Okay, here, I summarize again what is in the heuristic algorithm. Doesn't guarantee anything. DP is not a heuristic algorithm. DP guarantees that given your scoring system, you will have your best scoring alignment. This type of algorithms don't do this. Hopefully you're doing pretty good, and if you're really lucky, and if you have a good algorithm, then in 90% or more, you will indeed get your best possible answer. But that depends really on how you craft your heuristic. So, when we talk about vast search spaces, this issue of NP completeness comes up, and basically you can think it's not the same thing. By the way, if you want to be rich, well, do you think $1 million is still a lot of money? Okay, if you think so, then correct this problem. There's a Canadian waiting for you with a bag of money. He'll give it to you. But it should be the proof that, that you solve the NP completeness problem. Basically, dynamic programming goes with 2 sequences. Well, it's a quadratic algorithm, we talked about it. So if you get an exponent with your variable, the number of sequences, the number of letters, the size of your input, if you have a situation like this, then that's a bit bothersome. Yeah? So, first step, I'm going to show you what doesn't work in practice. So I'll be quick. But these were the earliest programs, because databases were small in those days, and if you have your 30 sequences, maybe you can do it in not a very, very fast way, and you're still okay. But if databases start growing, that becomes difficult by the time. And that is called multi-dimensional dynamic programming. And the idea is very simple. If you do it for 2 sequences, you have a square matrix. So what do you do if we have 3 sequences? A gentleman by the name of Murata from Japan thought about this. What do you get? This ID, right? 3 sequences, so we don't have a cube, but we don't have a quadratic matrix anymore, so take a cube. And now the pathway is something going through 3 dimensions, right? So I talk about, this is sort of a sausage in 3D. Yeah, so this path is something that goes through space, right? If you want to look around your path, I talk about some sausage. And when we go to more than 3 dimensions, for the normal mortals, it becomes more difficult to visualize that, but then you can talk about a hypersausage. So for us, a pathway through space will from now on be a hyper sausage. If it tastes well, I don't know, but it's for the line. Okay. But then, what's the complexity of this algorithm? From 3 sequences. It was x squared or n squared, doesn't matter, when we had 2 sequences. Make your guess. 3 sequences. What do you think? N power 3, perhaps? So 4 sequences, please. Are you getting worried? N power 4, 10 sequences, N power 10. So this is the bad news. This becomes relatively slow after time. Yeah, and databases now, when people do predictions from genomics, they want multiple sequence alignments. Let's start with 500 sequences to have a quick look. No, I wish you good luck with such an algorithm. And not seldom, it's 5,000 sequences you need to align, or even 10,000, and I've seen 15,000. Well, then all our programs we've made, they say, we don't know how to do this anymore. Because everything with this, if you build this memory requirements, scales in the same way, by the way. So you need a really big computer to get this going. So what did people do? They realized, and I showed this, you're using this cube again, and this sort of, extends over. Any number of sequences, basically. If you have your hyper or the sausage, it's here, the pathway, you can do the projection on each of the pairs of sequences. Do you see that? So if you have 3 sequences, you can compare sequence 1 with 2. How's that doing? 2 with 3 and 1 with 3, right? And so you have all those combinations if you have more sequences. But you have 3 pairs if you have 3 sequences. That's how it scales. So what you can do is, if you have this sort of sausage, then you have your pathway, in each combination of 2 sequences. And this one, you've calculated this. Right? So what's the idea? How can you gain space? The idea is, we have to, this is vast. We need to make a shortcut. So basically what we want to be able to say is, look, you don't need to look here in this corner of the matrix. This is all serialized if you don't want to look there. But how do you establish an idea of where to look or where not to look? Where do you draw the line? That was a bit of the point. And they do this basically pairwise. They say, okay, the best, this one when it projects, so we don't need to look around here. And if you do this for each combination, then you can sort of cut out a lot of possibilities. So you don't need to look there. And that makes your algorithm quite a bit faster. But still horrendously slow compared with the later techniques. But that comes in a moment. So if you consider 3 sequences, basically, as I said, you calculate all possible pairwise alignments. So 1 against 2, 2 against 3, 3 against 4. What is the number of combinations again? Do you remember? Something that's good when you really know that. If you have n sequences, how many pairs are there? If you want to do all against all comparisons. It's a formula, it's better when you know it by heart. So I write it down slowly and then it sits in your mind forever, I hope. Okay, so n times. So what is this? What's the size of this matrix? How many cells? You know that, right? That was n squared. Remember? If n is this n by n, and that is n squared. So this formula, I make a mess already. Go here. Is, well, what is it? It's half a matrix. Why do you only need half? Because 3 and 1 and 1 and 3 is the same pair. So with this cell, you don't need that one anymore. And which comparisons are you also not interested in? Self-comparisons. Where are these to be found? Well, that diagonal, right? So do you need something like n squared minus what? Divided by how much? If you got a feel, then I write it down. So if you say n squared divided by what? Divided by 2, you're wrong. You're not too far. Why? Because you give it a bit of the diagonal, you divide that by 2. So you should take away the diagonal. And then half. So what is that? This, a little bit less. That's your formula, okay? N times n minus 1 divided by 2. Now let's check whether I was talking out of my backside. When I said if 3 comparisons with 3 sequences, do this formula. If n is 3, what will the outcome of this formula be? I hope I'm right. 3, right? Yeah. Okay. And for 4 sequences. And for 10 sequences, 90 divided by 2, 45. So this grows quickly, but this grows basically quadratically as well. So it's not too bad, right? So that's why you can do that. This is already much less combination, much fewer combinations, of course, when you do all against all, then something exponential, right? That's the bad news. This is still within check, you might say. If you wait a bit by a computer, you'll be okay. what do? You take sort of a, but you know, you do that, then you have these pathways, and then now we need to select, you know, where to look in each square matrix, each pair matrix, and where not. What they do is they take a box standard multiple sequence alignment off the shelf. Well, you have to have one. If you're the first program, there's a bit of a problem, of course. They don't have it available, but they use the simple way of aligning it, a bad alignment, and then said, okay, all our alignments that we make should at least be scored better than that bad alignment. And that was their sort of cutoff. And then they checked in the matrix to say, okay, here, then we look here in the matrix, and there's no need to look beyond that. Right? How do you do this, guys? Do you remember how your cell is built up? How each cell was built up? You remember that, right? What does each cell mean in a DP matrix? Was the best score, your alignments, you evaluate it like this, right? And this is the best score of this bit of sequence still here, and this bit of sequence still there. Yes, the best score, given your score. So how can you, and in the end you have maybe a nice pathway that goes through here. And now we want to sort of say, okay, you know, there's no need to look there when we look at the score. You can think of a trick to do. How does your score build up? If you start here, what happens if you have a good alignment with your score? What kind of numbers are in your matrix? 6 and 4 and -2. And a gap costs you, I don't know what you did, let's say 2 points, 3, whatever. So this goes up by, you know, this scored like 3, 7, here it might be 20, and here it might be 50. And so it tends to creep up. Of course, it can go down, we know all this, right? Mismatches and gaps. But in the end, you will hopefully have some positive score. But if there is sort of similarity, then your score will, you know, will be something going like this perhaps, but it tends, of course, to creep up. Yeah. So, how can you now use this then to say, okay, if we talk about this, you know, here's your line, no need to look here. Okay, I'll give you one little trick you can think of. Yeah? So, what was this cell again? It was the best alignment starting here until this point, right? Whatever the alignment is, that's guaranteed the best one. Now think about a moment, suppose you would reverse the sequences for a moment. Run that same algorithm. So, if you would do it, so what do? We say we now run the sequence like this. What will now the value be in this cell? The best possibility of all alignments started here, so the rest of the sequence, right? So if you add this score plus that score, what have you got? The cell, all pathways, all possible pathways through the cell, whatever it is, will have the best scoring. Hey, if you could use, right? So it gives you, it's a bit expensive, I know. It gives you a feel like how you can use it. But you all look a bit worried. There's nothing to worry about. Even if you don't get a thing here, it won't affect you so much. It's just one possible way of estimating. You can do this in cheaper ways, but this is sort of a more or less fundamental way. It requires you to do what do you need to do to make this happen? You need one matrix where you score all the forward, like you do, your DP matrix. Now you make one other such matrix, but run everything from the top or reverse your sequences, but then you need a bit of a tally. If you just run against this, you start here and do the same thing, then you add up the cells in those two matrices. Yeah? The same position. Then you get the best possible score. Yeah? This will come back, by the way. I'm not telling this only for this, because I hope that in the HMM lecture there will be a moment that I'm talking and you think, oh, hold on a moment, I think I've seen this before, right? And I basically hope that then it will become easier for you. Yeah? I don't give a damn whether it's easy. It feels easy now for you because it doesn't fit so much. Yeah? But then it will. But yeah, this is basically then going back. They use and so if they have a good score here and they find the box standard score and then they say, you know, oh, this score is hardly any better than the bad score. Then you don't need. This is guaranteed the best score, of course, right? The question.
Well, I don't understand why this is faster if you have to calculate every cell from 2 sides instead of
it's
one.
Twice as slow as what you do, right? Because you do the work once more.
Yeah.
So yeah, that's what it costs. But that's for each pair you do this, right? You still have a quadratic scalability. So this algorithm will just be twice slower than the thing you built. Right? That's okay. You know, compared to what I'll show you, what you can do with this sort of technology. Then, but anyway, take the point that you tend to say, okay, I'm only looking into the hypersausage area and I don't look around. And that means you don't need to check and do your dynamic programming, your multi-dimensional dynamic programming over all, including all of those cells. And that cuts back the possibilities quite a little bit. Yeah? Okay, so that's the idea. Now, then, this is fantastic, you know, and computers have been so fast. So, you know, when it started, it was really doable without, you know, running a month or so. You could align 7 sequences. That was brilliant, right? Now, and they were 30 years ago, and what's this program? 80 something. It's somewhere on the slide. Earlier on. So after all those years, computers have become much, much faster now, you know, with a bit of work. If they're not too long, the sequences, then you can run 9 sequences, right? Is that practical? No, it isn't, because, you know, we need 500 and 1,000 sequences. So that is not working. So there was another clever guy, Jens Toy from Germany, Bielefeld, mathematician, and he thought about another way to make the search space even smaller and becoming much faster than this other program. By the way, you know the word pamper. What does that mean? It's another little fact here. A pamper is, what was the old-fashioned word, certainly in America? It's called diaper. Does that ring a bell? So pamper was a type of diaper, trademark for diapers. But they've become so widespread that everybody now uses trademark pamper as just a general word. That happened also in multiple sequence alignment, because that first program I just talked about, this one was called MSA, multiple sequence alignment. And then people said, well, this is in fact a good name of what we do. So people started using that term. And now multiple sequence alignment is not that program anymore, although it's still there, but everybody knows. It's a general term, right? This lecture is called multiple sequence alignment, and I talk about more things, hopefully, than just this program. All right, so the other one, Jens Toy, he started thinking, you know what, how can I easily make a problem smaller? You chop it up, so that's a lesson for life as well. If you have a big problem, I think I've told you this already, you try and partition it in smaller problems, the big problem in smaller problems, and if you still feel unhappy, you try to partition each problem once again in smaller problems. Then you've made small problems, but you feel hopefully a bit better. You can solve each of those. And then you combine the solutions and have a main solution for your problem with a bit of luck. That's also here. So what they do, they say, you know what, if we can make a good pivot point where I chop the sequences, like in the top one there, the blue and the red ones, then you need to just align the blue bits and the red bits, and these matrices now start shrinking, right? And if it's still slow, you know what? I subdivide once again. So then I use only the dark blue and the lighter blue there, and the matrices become smaller and smaller. So what do you do in effect when you look at in 3 sequences? If you would cut each of those 3 sequences right in the middle, you would get this situation that you only, so this is the cutting point here in 3 sequences. And then you only need to do this sort of sub-cube and this sub-cube and all the other ones. So how much does this save you? This is 1/8, I think, to the third, 1/2 to the third. Well, that's not bad, right? But now think about it, how do you do your cutting? That's a bit of a, where do you cut, right? Because what does it mean that you cut sequences in a place? Where will all those pathways go through? All the way through there. So the cutting point should be well placed, because otherwise you drive your alignment out of position. Right? So how good is this? You know this now by heart, so this can go. So in 2 sequences, if you have a nice thing in the middle, it's the same thing. What do you need to? Then you only need to look here, right? Forget about these. So this of course becomes better and better with multiple dimensions. But what if my cutting point is not so good, and I would put it like here? How much does that save us? Is this still as good as before? No, because now your matrix point will be sort of like this. So you only lose this one and this one. So if your cell is here, then it's hard to. So you have to push it in the middle somewhere. You want to do well, but you need to. So that's a bit of a problem, and you need to calculate again pairwise and do this cutting. But then it works. But you know, I'm very happy to tell you, I don't even have it on a slide. with this great program, it's so much faster that if MSA allows you to align 9 sequences, this one with a bit of luck might allow you to do 10 sequences. So that is just really so much faster. So, you know, this is cumbersome stuff. Do it in all complexity. Well, even with, and now basically these alignments have become even, these authors don't want to say it, but they've become a heuristic. Because it might still be that if you chop it up wrongly in both methods, hey, your best solution isn't there anymore. So they call them that, you know, they're looking into all combinations that are clearly done. So let's say, in the practical sense, out of the window. It's good fun, by the way, to try and calculate, to make, if you have really sort of weekends free, you could try, make an aligner for 3 sequences, right? Because now what happens with your gap penalty? The notion of an open penalty. With 2 sequences, what is an open penalty? That was when the gap starts. 1 minus signing 1 sequence. If you have 3 sequences, how can you start a gap? It can be done by opening a gap in 1 sequence, but you could also open a gap perhaps in 2 sequences. Or you have a gap running in one of the sequences and you then decide to open a gap in another one, right? So what is a gap penalty now? And all of these choices sometimes, you know, even if it's a great idea, can make that you think, oh my God, now I get so many arbitrary choices that I don't know what to do. So if I choose it wrong, I know it will very much affect the result. Even if it's brilliant, let's not touch it, right? Because I don't know how to handle it. So that can even happen. Huh? All right. So the main ideas, and this is a term I would really dearly, I'm even asking you a lot this lecture. I want you to memorize of this even, and times n minus 1 divided by 2 you need to memorize now. Sorry. Term, of course, progressive alignment, because then we talk a lot about this. It's all progressive alignment, and there will be 4 steps that will come, and I would like you to memorize that. And I'll tell you that these 4 things, there is a 98% roughly calculated over the likelihood that will be questioned in the exam. Okay. And now one more fact. Some years, 50% of the students are able to reproduce those 4 thingies. Even when I tell them there is a near 100% chance that it will be asked. Did I tell you enough this year? Or what should I do to hire this 50% score? I don't know. But okay, let's see how it will work this year. I have good hope. Okay, so, yeah, we're interested in families that are evolutionarily related. This is the near silly remark at this stage, because what do you say? Should we align sequences that are non-homologous? How does that work? Because what does alignment do? It tries to relate sequence back to the common ancestor. If you have no inclination that is there, then you shouldn't align it, but okay. But basically what you say is, you know what? We have this combinatorial explosion. We will build it up basically in a pair-way fashion. You know what? We're going to sort out what is easy to align, and later on we'll do what is more difficult. So what in your book is an easy alignment, where you're pretty sure that your alignment will be okay? Yeah, close sequences, near identical sequences, even better, identical sequence. Yeah, but then okay, that's not really giving you any more information when you align those. But so the closer the sequences are, yeah, the less widely divergent they are, the easier it is. Yeah? So these and different alignment in practice, different alignment. If you have 50% or more identity, you don't need to think any program will be able to do that. If you create a program that cannot do this, I don't know how, and then you're very clever. So here come the 4 steps, okay? We do, and you've heard it already. First, all against all pairwise alignments. How many are there? The formula was here a moment ago, which you now know. Very good. Then you align all those. You take the alignment scores, then put all those pairwise alignment scores in this matrix, and here you see that number of combinations. ASA matrix, not including the main diagonal. I'll come back to this with all kinds of methodology, but not now. These will be 2 separate lectures later on, called phylogeny. So there is a method to sort of show you which sequences are the closest. And I think, you know, this is, you'll be able to really tell, you know, how you should interpret these type of pictures. So basically, A, B are related sequences. That's how you interpret this. C, D are related sequences. What about E? This sequence is called an outlier when we call it this tree, because you see only in the very end. And where is your common, your universal common ancestor for these 5 species? represented by these protein sequences. This is where the stuff starts. This is a long time ago. The time progresses basically. You don't know with what steps, but this is how you can interpret it. Yeah. So that's great. So okay. What can you do? What have you prepared now? You have made last night, or what was it? Was the deadline, I think, or on Friday even? I don't know. The deadline
It's for
VP,
next
you
week.
did. Next week? Oh, sorry.
Yeah.
VP's next week.
Oh no, that was
No.
yeah.
Done. You did it.
Yeah.
You should feel happy. You made something. You created something. Why are you not more happy than you seem to be here? You've made something great, right? Are you worried about the score or something? I don't know. Oh, anyway, no. But let's assume that you are able to align sequence A and B now with your technology, right? And that's great. So you need to do that in the tree. This is progressive alignment. What do? You have the guide tree, and then you follow the order in this guide tree to build up progressively your multiple alignments by adding sequences one by one. So this is great. This is easy. This is easy. You can do this. How about this one? That's the next slide. What do we do? What do we need to do? We need to align two blocks of sequences that each contain two sequences that have been pre-aligned by your programs. Right? So we have CD aligned and AB in that tree, and now we need to align those two blocks. How can we do that? So, as I said, you know how to do this. But what kind of situation have we now? That here there are now two sequences pre-aligned, and there are two sequences pre-aligned, and we need to think of something. Who has an idea? Think about. I heard a good word. Say that again.
Consensus.
I just would like to say, think about politics, right? So consensus. Okay, is that easily reached, the consensus in politics, you think? So, but yeah, so historically, people were very positive. They thought, pull it off like that. So, consensus sequence. And I'll talk about it a bit more. And here you see that word coming up. Profile, right? There is an inkling in your mind already, I think. But let's do it. Let's first do the consensus sequence. Just two sequences. Here they are. This is the alignment. No gaps, doesn't matter. And now we will define the consensus sequence. So, the first position, easy, right? It's F and F in each of the sequences, so it doesn't take you long to decide that your consensus symbol should be F. What about the second position? What are we going to do? What would you do? Ignore it, so put an asterisk in, but then you don't have information. So, come on, choose. Anybody?
Can we extend the letters to add letters that
This happens too. Extra letters like the AV letter, A or V. Yeah. Say that's not allowed for now. So give me a letter. Which one would it be? Then you could say, okay, let me pick A or V. And then you could look in your multiple line to say which letter is the most abundant. I pick that one. Would there be another way? Suppose one amino acid in the one sequence is a very tiny polar one, and the other one is a huge tryptophan or something, a huge apolar one. Pick one, you know, they're fighting. What do we do? Maybe then it's better to use that's also what a consensus means. You pick something else that better represents both letters you find. So how about that? It's Monday, you have to wake up still, I know. But, you know, have you heard of what's it called again? A blossom matrix? You remember that? Suppose I say blossom matrix to you. How many possibilities are there to fill any letter at this place of the asterisk? I'll tell you, 20. Right? 20 amino acids. So we could try all of them and score them. How could we score a possible letter at the asterisk position? I'll tell you, say that letter is for now in the tryptophan. I look up in the blossom matrix the WA, the tryptophan A distance, and the tryptophan V distance. I add them up, divide them by 2 to get the average value, right? And you have a number. Now you do this for all the other possibilities. Which one would you pick? The highest. Brilliant. Now you do this and you're very happy, you feel clever and so on. But next Monday, very angry biologist will storm into your office. What a ridiculous method have you made, you know. Because I see letters and then you say consents and I see a letter that's not even there, right? And what do you say then? It's not a bug, this is a feature. I'll explain it to you, okay? That's how bioinformaticians try to save their body from all kinds of bad things. And computer scientists do this too. It's a feature, it's not a bug. Okay. Anyway, so consent. And what's another problem? If you have a column where that is totally conserved, you get a letter. If you have a column that is totally unconserved and is a big fight, you get a single letter. Because census sequence is not showing you any trouble or any further information about that alignment. We throw a lot of stuff just in the waste bin. That's not good. So what should we do then? So the idea was, you know what? We should need a representation of a sequence alignment that holds more of this information. That tells us about the frequency or the likelihood of a certain amino acid in that alignment position. And we've talked about this at various occasions already. PsyBlast, for example, right? They're doing this. I can show you how the profile is exactly built there with log2 scoring. And so here I go a bit into history because that concept of profiles, run it past you once again, goes all the way back to 1987 when Michael Gripskov, Lachlan, David Eisenberg were the first to do this. They said, okay, we're going to put in a likelihood of each alignment position. We take a column, 20 positions, and we put in the likelihood of each amino acid at that position. So we get the sense of, is it totally conserved? Then you get a high likelihood for a single amino acid. If it's not conserved, it's more spread, the likelihood. And then they already inserted an extra row. So in each column, position 21, to put in an adapted gap penalty depending on the situation in the alignment. And they did it a bit funny. I'll show you that picture here. This one then, and then I go back. Here is an alignment where it's white, it's gap, right? And here you see nicely aligned gaps, but in reality, of course, you see very often that these borders are not so nice and straight. So what these first people did, they said, okay, I look at each position. Is there a gap in any of the sequences? Yeah, here is one. And how long is that gap? And they said, if that is very long, so you pick a position and you say, oh, that gap in this case doesn't matter which one you pick. But if one would be very long, stretch all the way until there, that gap would be used as a weight. And that's how they did it. And then people said, well, nowadays that's not done anymore because that's not so stable. People tend to now look just per column and say, what is the frequency of gap? It's a symbol almost. So here you can say, okay, half your positions in this region have a gap. Now suppose I would like to align a short sequence, right? To this alignment. Where would you like having this? Where would you like the gap? If it's a short sequence, you know one thing for sure, there will be gaps to align it against this alignment, right? You have to. Placeholders, where would you like these gaps to land? And then you might say, well, given this clear image, I would like the gaps in the middle again. Then I have also conservation of gap placement, right? Maybe that's a good thing. And then you can say, okay, what happens, happens. But then you might say, no, I would like to enforce that a little bit. Can I tell the sequence, if you make gaps, try and stick them in the middle. How can you do that? And then this 21st position comes into play, and here you see some idea about that. If this is your normal, you have gap penalties, and then you have a weight, and your weight normally is at 1. And here you say, you know what? Whatever I use as a gap penalty, whatever the user takes as an input, I'll have that value. I'll apply smaller gap penalties, so I'll penalize gaps less when they are in that middle region. And then the alignment thinks, a gap is not so much of a problem because I paid less, right? So the alignments will be favored to try and do it. So that works. Okay, so this is basically a profile. So in its easiest form, a profile just holds the percentage or the fraction of the amino acids you find. You just count how many A's, how many C's, how many B's, and you calculate over the 20 positions, just the frequency in each alignment column. And then you can worry about this extra position 21 for the gap penalties. There's no clock here. I feel it's coffee time. Am I right?
Yes.
Yeah? Okay. Break up. Let's see. I want to finish. Yeah, I'll finish the profile. You start thinking, in the break, how can we align this? Because this we should be able to do. This is aligning a sequence against the profile. How could you score that? If I would ask you, put that in your program, how long would that take you? How would you do it? 3-1, by the way, so I'm not trying to just numbers. Before, remember, you did something where you came either from the top or from the left, and you inserted the gap score. Where you came from diagonal, it was about a match or a mismatch. And you looked up a number in a Blossom matrix and filled that in, right? That's how you build your program. So how do we do this now? Now this is a multiple line, a pre-aligned block of sequences against a single sequence. How do we do that? Anybody worked it out during coffee? You didn't bother, I think. So I'll tell you that. Okay. Don't worry. So here is just one cell in that matrix. Over here. Means you align a symbol in the single sequence, so that the red L there, against a position in that pre-aligned block of sequences. And that's, let's say, the blue column there. These amino acids are to be found. So in its rudimentary form, the easiest form of a profile, just calculating the frequency of the amino acids at any position. Here you get it. If there are 2 A's, 2 V's, and 1 L, your frequency relationship is like this: 0.4 for A and V, and 0.2 for L. And you can always easily check whether these numbers make any sense by adding them up and checking whether they sum up to 1, right? That's what statistics demand, and that should also take place here. And then what do you say? Normally you would say you would, for example, align an L against an A. What would you do? You looked at the LA score in your Blossom matrix. Now you do nearly that, but you need a few more lookups. And you say, okay, now I don't compare my L against a single letter, I compare it against 3 letters, but I would like to weigh in the frequency of the letters. How do you do that? Well, very easy. We call that weighted average. So basically what you say is, okay, if I compare my L against the A in the blue column, that's 40% amino acid, it's there. So that's the 0.4. That's the weight of this. When I compare the red L against the blue L there, great Blossom score, of course, but it will count for just 20%. Yeah? And the other one against the V, which is also 0.4 amino acid. Here is your weight, 0.4, right? And and that's what you do, so that's weighted average, using a profile. So you do this, and then you just have this as an extra line of code. Yeah. And then you fill it in and your alignment runs like nothing happened, right? So you could easily do it if you want. But that is, okay, so we learned this. But now, of course, we are able to align a sequence against a sequence. You can already do, with a bit of work, you will be able to align a sequence against a profile. What's the next step? Aligning 2. Already we had that problem up, right? 2 sequences against 2. So that's this problem. Sorry? Microsoft Word, I don't mind. I mean PowerPoint. Oh, now my whole computer is getting angry. Don't send. What is happening? Hello? I can't blame you, right? Because you're reading this thing on another. Okay. I think I'm in my lecture again. Now let's see. Yeah. Nice mountain. Okay, yeah, there we go. Good. So, how do we do this? I send you again in coffee and then you come back. Won't work because, okay. So, how do you think? I'll tell you the secret once again. Weighted average, but now a little bit more weighted. Because what are you going to do now? Here's a simple example. Now this L in the sequence is also now in a pre-aligned block, and it's only part of it, so it has an A and L. Oh, this is the old one. This is another block. So this is the weights there with 4 sequences. So 3 times G, let's say, and 1 times S gives you that frequency relationship, right? And what do you do now? You just go against all. So you align the one in its proportion to the other ones just like before. So the formula is now a little bit longer, more terms. How many terms? n times n minus 1 divided by 2 terms, I guess. All against all pairs here as well. And no, is that true? You should correct me when the teacher makes an error. You should sternly reprimand him in this case. Because here it's not a combination, it's an L in the one against maybe an L in the other as well. So it's just 400. It's 20 times 20. Yeah. Okay, but anyway. And then you have just all, so it's the point, this is the A against the G, so you look up the frequency of the A, that's 0.4 in blue. And the G there, it has a frequency of 0.75, and you multiply these two, right? What do you do with a letter if it's not to be found in any of the weight? Then the weight will be 0, and that term will drop out of the equation. Okay. As a test, what if I would put all the S values here to 1? What will the outcome of this formula be, you think? Let's also test if the statistical world is still running for you. What do you think? What should that become? 1. Magic, huh? Should be 1. Because it's a weighted average. The total weight should be 1. Okay? That's how it works. So this is for profile against profile. So if you do it like this, there are other ways as well, but this is a simple way that works, and a lot of programs use it like this. Then you're able to align sequence against sequence, which you're doing already, sequence profile and profile profile. That is what you need to use any preset block if you pairwise build your alignment. So let's go do it. So basically, okay, this is all saying what I just told you, and here you have the thing in general. So this formula that I just showed you is, if you want to put it a bit more mathematical, and here you see the 400 coming up. One runs over the 20 amino acid. The other block runs over its 20 amino acids, and here is the frequency of the one amino acid type times the frequency of the amino acid type you're looking at in the other block times that blossom score, right? Or any score in any exchange matrix you care to choose, right? And basically, what was that score? And this is an earlier lecture. Do you still sort of remember that? But these were the values in these blossom and all these matrices. Basically, the real evolution model offset against a random model, a null model. So what do? You have these log values in those matrices. So there are some methods that thought they call that log averaging. They take the log away from here and put the log before. This is another way of weighing in the frequencies you get out of it, right? What is a log doing? What is going bigger becomes, you squeeze it down a bit, right? And here you find, these weights are used more now when you log it here, right? It's another way, it scales a bit differently. And some people say, this is certainly the inventor of this shouted, this is the best idea ever. You decide whether you agree. I was not so totally impressed as that author himself, I must say. But okay. So, the 4 steps once again. These are the 4 steps. 3 steps. Pairwise, use the alignment scores. Number 2, to produce a dendrogram. Number 3, and then align the sequences using that order in the tree. These are the 4 things. Your 4 o'clock moment. I'll wake you up. You tell me the 4 things, and I'm out of your wherever, out of the room. So there are quite a bit of methods that are. So Biopat was in Holland, Paulien Hoogeweg, the inventor of the term bioinformatics, you might say, in Utrecht. I've shown you that. Also made a first program, Biopat, multiple alignment. Yeah? David Sankoff, a Canadian, was maybe a bit earlier, half a year or so, with the ID, but Paulien already was building a program. It was called Biopat. Willie Taylor very early on made a program. Wes Higgins was in. Crystal was there earlier, but his enormously cited paper was 94. And this is something I was involved with when I was in London, and this is the one we're still sort of developing in our kitchen here in Amsterdam. So it's okay to criticize, don't mind, but do it carefully, okay? All right, so here are, in a way, the 4 steps again. All against all. So if you have 5 sequences, what are these n times n minus 1 divided by 2 combinations? It's 1 against 2, 1 against 3, 1 against 4, 1 against 5, 2 against 3, 2 against 4, 2 against 5, 3 against 4, 3 against 5, 4 against 5. That's it, I think, right? These are the combinations. So a computer program runs in a double loop. So you have that, then you fill in the similarity matrix using the scores. Maybe you convert into a distance matrix, the distances, there's a conversion, depending on what the program wants to make a tree. And then you have the order, and this tree clearly establishes first align these sequences, then these two, then the block, 2 blocks of 2 sequences, and then 1 sequence against the pre-aligned block of 4 sequences, right? That's how you do it. And then you, so it means you pile up your alignment. One program is even called pile up. You know, first you have this, and then you have that, and then in the end you have your multiple alignment with the 5 sequences. Okay? So it works a bit like this is the order. You start, you do your first 2 sequences first. Where it's red, you do. Where it's blue, you do. No, what's red, you do. And it turns blue if you've done it. That's, I think, the idea here. And so 2 against 5 there. Oh, your pre-aligned block was 1 against 3. That's why the block is blue. Trying to understand my own slide here. Okay, it works. And so now you align these 2 blocks, and then in the end you align this one. That's your whole thing. So in the end, when you've done all of this, you have your alignment. After the first step, when you align sequence 1 against 3, how many entities have you got? N minus 1 at that moment, right? Because you have 2 sequences aligned and 3 loose sequences if you start with 5. And here you have 2 blocks, 1 aligned, 1 pair, and another pair, and 1 loose sequence, and so on and so forth. Okay. Praline is doing something else. So this is, how does this work? You calculate this tree before you do anything. You have the order, you follow that order diligently, in principle. And Praline, we said, no, not going to do this. You know what? We have all these sequences, we say, what is the best? Now, what is the best scoring one? Let's start here. Okay. These 2 sequences. Okay, we have that aligned. 1 entity, so now I look at all possible alignments, and then I pick the best again. So basically, you build a tree on the fly. The tree is not there at the start. You build it on the fly, so at the very end, you have and your complete tree, and your complete multiple alignment. Okay? I'll leave that to you. You can read the paper if you want. So, how reasonable do you think this is? Is this total crap, this method? Let's go to the classical one, or now to this picture. What's the information you put in? What does the algorithm, what does it use? It uses information about pairwise sequence initially, right? Then it recombines them. One thing, what do you think happens if this is aligned? If alanine 31 is put on variant 42 in the other sequence between 1 and 3, that is here, that alignment will stay there forever, right? You're not going to change anything anymore. I can tell you, there are 3 geniuses in bioinformatics, I think. They're all 3 a bit crazy, it has to be. One is Alexa Merzin, that will be in the next course. He has 200,000 protein structures in his head. Believe it or not. And you say that one, and then he said, yeah, but the look there is a bit more, and he's always right. He's a horrible person. He's very kind, he's Russian. But he's Alexa Merzin. There's been really a seminar with serious people who said what happens after Alexa Merzin gets under a bus. Because what happens, people say, Alexa, you should teach us. How do you do this? Because he's better than any prediction program. Well, that's a good thing. So you think, if you could tap his brain, and it can't be that complicated. The guy's intuition, right? It must be. He's not looking over these and do them all because then it takes 2 days and his brain is faster because he's. So, I mean, that didn't want it because he likes this. So maybe it's just a little trick. I look at this side of the protein and then a little kinky there and then I know and don't tell the others. Maybe it's that. I don't know. Somehow I don't think it's that simple, but anyway, Alexa is not telling his secrets to us, so we have to go on with our sobering activities. Okay, anyway, that's one. The other one is Amos Bayrach, sequence databases, the Swiss plot database. I was in the lab that he visited once a week, 30 years ago, 25. By 80,000 sequences in the database, and I think that's a lot of sequences, whole file with annotation. He would stop seminars, he said, no, that's not the case, the protein doesn't have an L in position 64, it's a V. You think, come on, everybody in the database. Oh no, you're right. He had a database in his head again, so not structures,
sequences and information. 80,000. Why do we know? Because at 90,000, roughly, Alex has sat with a little laptop in the interview laptops and looked up sometimes to check himself. So then we know, thank God, he is mortal. His brain is big, but luckily, So 100,000 was even the upper limit of Alex Merson. Now, the third genius in my book, I need to tell you, it was a man. He's not there anymore, it seems. He was a Brazilian. I've never seen him. But people told me this guy is doing multiple alignment on a sheet of paper. How is that? And it seems he would write down and sort of sequence, he had it all done, and then he would almost write it out, but sometimes they said he would say, do differently because. And that is, so what did he do? That is something that these programs are not doing. He aligned stuff and then he said, oh, I did this, but now I see here, then it's better to reorganize it, right? So you get back on earlier decisions. You change it because you find out later that that is better to do. Now, this sort of intelligence is not in this program. It does it, it follows the order dictated by this tree, and it's just going from, put the sequences on top, 2 sequences, you line that at the best, but what has happened earlier on is not changed. Yeah? That's a very important thing. What's the other thing? I already asked you. Let's talk about something positive on this methodology there. What's easier to align, distant sequences or close sequences? Close sequences. Where do we start here? All the combinations with the close sequences. So if you align close sequences, the chance that you make errors is lower. Yeah? So in that sense, it's reasonable that you do this. And that's the idea. Yeah? You need to do something and then you follow, because I can tell you, most computation sits in making this tree. We can talk quickly about it, maybe there's a slide coming up next week, but okay. How many combinations of pairs we need to align? N times n minus 1 divided by 2. Okay. That's quadratic basically, right? So then you do all of this, and then the whole algorithm here, and it's also taking time to make this tree, then you follow the... And then, when you have the tree, how many steps are there to build the alignment? How many steps is that? Count for this. Here are 5 sequences to be aligned. How many alignments do we make when we have this order? So we count 1, 2, 3, 4. Is that quadratic? Abstract a bit away from 5 sequences, 4. What kind of mathematical formula do you think that is? N minus 1. Brilliant. Very good. Okay, so this is quadratic to make this thingy. When you have it, it's just n minus 1, linear. So this is a lot faster, well, depending on how much time it takes. This is line, that is line. So making the tree is expensive. So they would say that this better be good, right? And be usable. So there are people who say, you know what? I don't mind the tree so much. Even if it's a bit off, I don't care. Alignment works well enough. Then you become much faster. So I give you one inkling. Willie Taylor, what did he do? He said, you know what? I take my 5 sequences, I count for each sequence how many A's, how many C's, how many V's. I have my frequency vector for each of the sequences. I convert those for each sequence into a 20 vector, having just the frequency of the amino acids in each of the sequences, and I align the vectors, or I compare the vectors, and I make the guide tree of that. Not even doing alignment, right? Just comparing in an order. That cuts back things. But if you believe here, it is really the thing, way to go, then you really need to make a phylogenetic tree by using sequence alignment. Okay, anyway. So here is what I just said to you, and this is also, you don't need to remember, but you will even if you don't want. So it's Doolittle. The man who didn't do little, he did a lot, but it's called Doolittle. And he said once, and this is really telling, you never get back onto take a decision. So once you put in a gap, once you put in a match or a mismatch, then once you get, always you get. Yeah? Alignment is doing nothing else than placing gaps, by the way. Yeah? You worry about matches and mismatches, but if you just know where the gaps are, you have your alignment as well, right? So that's the other side of the medal. Okay, so that's maybe not good. It's a so-called greedy algorithm. It does the first thing that happens, and it does the first thing that is, and it's never thinking back and re-evaluate choices made. Yeah? Okay, so I've shown you this slide before. This is about how reasonable is it that you do the easy ones first, near sequences first. Well, this is the error buildup, and you know, errors progress pretty dramatically. You see, you know, when you're in the twilight zone at 20-30%, a lot of this is the error rate, so, you know, 30% is correct of your alignment, so you make a lot of errors. So you have to be very careful with aligning distant sequences. Where will they be in this scheme of things? Where is it difficult? The further back in the tree you get, right? This is just a small tree. Think about a tree of 20 or 30 sequences, then you have all kinds of branching and you know, there. But what happens? What do you know about the sequence? How much information of the 5 sequences do we use here, by the way? It's another thing. Just those 2 sequences, right? Do we use the information about the other 3? No. Where do we use the information about all the sequences, by the way? Is there a moment in time? Here. Then it's maybe too late. 4 sequences pre-aligned. Maybe errors in it. Sorry. This 5th one goes against it. Whatever is there. Yeah? You can pull your hairs out. Oh, I see now it's all wrong. So then this method is not helping you anymore. Yeah? That's what happens. What happens if you would still make an error here? What happens with that error? There should have been A on an A, but you put somehow the A on the W there in those 2 sequences. So this position is a bit muddled, right? What's that going to do with the rest of your alignment? It's driving it off. Error progression even. Early errors are taken with it all the way to the very end. So if you would like to avoid errors, try to zoom in on the early errors, avoid errors. But luckily again, the early steps are steps where the alignments are still close. Therefore the chance for error is less. So it's reasonable, but not more than reasonable, right? Certainly not ideal or optimal or anything like this. Well, maybe optimal, given that it's faster, but yeah, it's not great. Okay, we were here, we were there, so yeah, this is at the root, so this is this little problem, this crunching, you know, here we have this alignment now, and what should you do here, and these are the problems, and this is the basic algorithm, progressive alignment. So, lots of people are in this area, lots of paper widely cited, a lot of activity. It's really, you know, I don't know if it's a business you should go into, you know. There's so many people in multiple alignment, so to make a cracking program that's better than the pack is becoming harder and harder, right? We are a bit frustrated right now, because with Praline, we were on top for a while, and now there's Crystal Omega, and Des is such a nice guy, but I would love to hate him, but I can't, because he's my friend. And so his program is better. So now we're all doing new tricks and new heuristics and dirty business, trying to get better, you know. We need that one database where we can show that we are better. That happens too. If you can't win by fair, good, you just do a database selection, right? Have you done this trick already? Perfect. There are so many databases. Just like then, why do you tell this is a general, randomly database? We just selected randomly. Yeah, that's random is a wide sort of term, right? Anyway, so heuristics is just so dirty tricks. I'll show you a few. There are other things. So, what is the problem? Early errors progress. Also, once a gap, always a gap. Think about the first alignment we make does not use the information of the other sequences. Would there be a way to say, okay, I'm going to align this, can I look a little bit over my shoulder already to the other sequences, like what would they like, you know? How can you build that in? That would help. You don't need to get back, but maybe you can you use still at the early steps also information from other sequences? The answer is yes there, otherwise I would ask this question, of course. So there are even pralines doing it. But I'll show you, I think, the next option. Using information from even more sequences than you want to align. You want to align 5 sequences, but each of those sequences have in databases all kinds of homologous sequences. Hey, could we use those? Use it, see if they would make your alignment better, and then forget about them and show the alignment of the 5 sequences, but you know, maybe a more better quality alignment. So, an early program, there's this widely cited paper, which was it, 60,000 times, is called Crystal W. So the winner now, and there was Crystal X, and now there's Crystal Omega, according to Des Higgins, the creator of this series of programs. It will be the last thing he's doing, that's why he calls it Omega. So this is still, because of these citations, the the most well-known program. I see still papers coming from China and India, one journal I'm editing. But basically the program is obsolete. So if you go to the EBI, want to run a program, you cannot run Crystal W anymore. You're channeled to Crystal Omega. But anyway, so this is, you might say, just the standard progressive approach. So it makes a tree, follows the order of the tree, by piling up the alignment and so on. But then there is a heuristic in Crystal. What's the reasoning? Sometimes following the tree is not such a good idea. It turns out that sometimes the alignments are not biologically optimal. Experts tell us, you know what? We build in a little thing that sometimes we follow the tree and then we defer, we say, the tree wants me to do this, but I'm not going to do this. I do something else. I write down what I'm doing and then later on I get to the order of the tree. So a little bit of dirty business around the tree order, right? Also what they made, and that was also that made the day. We can answer, but I'll try anyway. Suppose you want to align 5 sequences. You get a multiple alignment. Okay? Now I put in, make another alignment of 10 sequences, but the 5 extra sequences are identical to the first sequence. What's going to happen to your alignment, you think? Will it be completely the same? You know, the first 6, of course, is the self-alignment. So you'll get a block, of course, with those 6 sequences that are identical. But what will happen, do you think? What do we use as information to describe pre-aligned blocks? Profile. Frequency of amino acids. What will happen to the frequency of amino acids if we have 6 sequences doubled?
Bias to the first.
You bias the frequencies. Do you want that? The answer can be no. What do you need to do then? You need to recognize it and weigh down those sequences that are more redundant. Happen more, right? So sequence weighting was the big thing for Crystal, and they put that in. And it worked in their hands. You know what? It is also a lesson in itself. So Crystal has developed over the years. So what do? You have a program, you have reference databases, you say, oh, it's pretty good, oh, now there's a better program, you do something, and you run it against one or more databases, and better. The order is just, all the ideas come in that order through time. So what did we do in the year 2000, when there were many tricks were developed by Higgins et al.? We had an inkling that sequence weighting, we had a hunch against it. So we said, we hacked the code, took it out, just looked at it and they became better. So their best idea early on, over time with more ideas, turns out not to be a good idea anymore. An idea, how good an idea is, has an environment, but also a time point, right? What is a good idea in one time is not a good idea in another time, Putting coal in your heating system was a good idea a century ago, but now not anymore, right? And then, good ideas can become worse, and then the other way around. So that happens. Okay, so what did Crystal do? Here are this. This was, I think, in the book of Durbin. I like his phrasing. He's always English and careful, right? So you could say they did dirty business. The Dutch would say they screwed up big time. That's our way of treating others. But here it was carefully crafted heuristics. Corner cutting, basically. So, local gap penalties, automatic selection of the amino acid substitution matrix. They said, hey, they tell us Blossom, oh, but for this is more distant sequences. You know what? I'll take a matrix that is built for more distant. There was a trick. I never got this really to work. They put it in. I don't, but okay, no, I'm not making this. I would have done it, but they did it. Automatic gap penalty adjustment. If you choose a more distant matrix, what should you do? You think with your gap penalties. If you know sequences are very distant, what happens with your scores you would like? What is the matrix doing? Should there be an identity matrix you use instead of Blossom? No, you want the matrix. You remember that story with the wall, the diagonal high, and then the bricks fall off. You need a matrix that is smoother, right? Your gap penalties have to go down. So they sort of work with this. Basically, it is the basic structure of progressive alignment with a lot of little thingies building, right? That is Crystal for you. Okay? Now, I told you already, the latest one is Crystal Omega. Basically, the big thing is there that they describe profiles as hidden Markov models. And I'm parking that for you a moment because there will be 2 lectures, important lectures by the way, on Markov models and hidden Markov models. And they will understand better how that is. Basically, a much statistically relevant description of a profile. And not just the frequencies, other weights, but probabilistic model of that. Okay? And they use another package that was already there. HH align, they use that to align groups. They used pre-existing stuff, didn't build so much new, but that's still quite good. So that program is still good. Oh, this is cluster W. This one is not there anymore. If you run it, you automatically go here and that's the cluster omega page. Yeah? Basically, what do? You enter your protein set in FASTA format. I think by now you know what it is. Protein baseline name, sequence donor. And you can select parameters if you want. If you don't know, don't do it. The default values are normally quite good, but it's fun to try anyway. Let's see. Yeah. Homework all those years ago. I should have stopped. The iteration. What is iteration? Well, Psyblast was iteration, right? What do you do if you iterate? You run a result, then you redo part of your procedure, you learn from it, then you redo part of your procedure, get a new result, and hopefully that is better. And then you learn again, and so on. Psyblast is an example of that. Who can explain to me what this arrow might mean? How can you iterate by doing this? Then you have to look how these numbers in the matrix come into play in the first place. What did you do? All against all, you make alignments of all possible pairs, take the score, fill it in. That gives a tree order, you follow that order diligently, you get your alignment. Now somehow, what can you say about this alignment? Are all sequences you think here aligned in the exact same way as they would be aligned as a pairwise alignment? What do you think?
No.
It's a good answer. So what could you say? You have these pairwise alignments, and they're brilliant, right? They're made with your program. You use the Blossom matrix. You know they are optimal. We know that, right? Best according to. So they're great. But what do you get? This is sort of a big compromise. You know, you cannot listen to all those alignments I tell you only when they're all identical. Then it's all not interesting. Then everything is totally consistent. But you will find that you have to sort of bend some of those alignments and change them in order to build a single multiple alignment. What does that mean? If you have such an alignment that is changed relative to their paired alignment, that alignment should score higher or lower. What do you think? Lower. It has to be lower because it's optimal there, high as possible. So this must be lower then. So, do you see the arrow? But still, it scores lower, but that's just according to some mathematical concept. The idea, of course, is that biology here is better. Lower scoring can sometimes be biologically more advanced or better, yeah? More effective. So, what do? There you had all against all against all alignment. Can you do this here as well? What if I would say, I take this sequence alignment as it's aligned here? Could I calculate the score? Sure. You use your matrix, match, mismatch, gap, you just score it. Could you do this for all pairs?
Yeah.
1 against 2, 1 against 3, 1 against 4, 1 against 5, 2 against 3, 2 against 4, and so on and so forth, do all the combinations, but take the alignment as they are here in that alignment. So that means, is this matrix going to be the same?
No.
No. Lower scores, basically. Different scores. Which scores are guaranteed the same? From the tree. Who can tell me that? Sometimes you ask this as a question on the exam. I can't do this now. I gave it away already. I could still do it, eh? Because half of you will have forgotten completely that I said. Where do we start in the tree? These two sequences. We call them sequence 1 and 3. What about this alignment that's built here? That's just a pairwise alignment, right? There's two sequences. That will be here. It's not changed. Once again, always again. So that alignment will be the same. Same score. Which alignment also? These two. Because you're aligning as a pair here. But then you go. And this one is 1 against those 4. So this alignment will be different, right? Okay, so that means different numbers. So that means then, if you, from this new matrix, you calculate the tree, will be a different tree. Different order, perhaps. And then you get a different alignment and you learn. Yeah?
So why would we even take the trouble to be all against all in making the tree? Why wouldn't you just align them singularly to each other and from that make them multiple?
Yeah, but how?
Well, I mean, it's probably high complexity, but
Yeah.
if it's limited to 5 sequences, then you could probably just do the multitude of every single possible alignment and then see
Yeah.
the
Well, that's a
multiple
good idea.
alignment.
Because, so you say do something box standard or something quick and dirty to make your initial alignment,
Potentially.
and then go whoop, and optimize yourself into heaven.
Yeah, it depends on how many sequences you have. Obviously.
Sorry?
Depends on how many
Yeah,
sequences you
also
have.
that. But no, this could be. The problem is, and I should add, it's good because I should maybe add one piece of information. This is what would you like to always have if you iterate, that you are certain that it leads to a better solution all the time. You're not here. Also with blast, you're not. And that means this is not a thing like start with some bad alignment and you go better on the way. Probably if you start with a bad alignment, it will make things even worse. So your initial alignment, your seed alignment is of importance. So I like the concept because it's quicker and it would use really the concept of iteration. The very start is too important. That's the problem. Yeah? But it's a very good idea. Okay, I'll still want to show you real alignment that you can sort of look at it and criticize it and agree with me that... Sorry, was that a question?
So, why doesn't the score of 1 and 2, why doesn't it change?
This is the tree. So this is sequence 1, 3, 4, 5, whatever. Doesn't matter, right? So this is 1 and 3. So you align them as a pair. You don't look at the other sequence, it's just a pairwise alignment. That alignment is now there. It remains like that. All the symbols, matches, mismatches of 1 against 3 will not be changed anymore.
But 1 and 3 are not in this multiple alignment are not aligned the same as in the pairwise alignment. Right?
Yes, it will be. Well, if you use the same parameters, of course. It will be a different alignment, but if it's the same type alignment, then it will be the same. And the point I'm making is nothing will be changed anymore. What you did is done. It's committed. Okay? So that's why you say there are 2 alignments and the others not. So what is not changed depends on how your tree looks. What about this tree? I'll show you one special tree. I don't know if you can still see it. You like this tree? Look a little bit. It's not to be straight, but you know it's a tree. This is called the chaining tree. Do you see why? If you do some nice pattern recognition, want to learn and get a sense of grouping, what do you say? It's not so great, right? Because all this time you add 1 to the existing group. See that? Compare this to a tree that looks like this. You think of this tree. This is what people tend to love, right? Why? You have a group of 3 entities, whatever it is, and here a group of 3 entities, and they're well separated. Right? This is how you interpret it. It's better separated than when it would look like this. Yeah? Okay, just gives you some sense of tree. But okay, let's go on because I would like to show you an alignment. So that alignment is this family, this is the structure. Next course you'll see a lot of those. So you see color coding, you see beta strands, and these are alpha helices. It's alpha helix, okay? Next course, I will fill it in for you. Here is a tree, and there's one nasty sequence I can tell you. These are series of flavodoxin, you see them all fluff of flavodoxin. Here is one other, this is a free kind, this is PDB code. Next course you'll know everything about that. Structural database. This is chemotexis protein. It's a distant homolog. You see it as an outlier. This is sort of related to that family, but in a very distant way. Okay? And this is a nice sort of family. You would like to make the alignment and make it happen. You know what? I'll show you the alignment already. Here we go. And so what is red? With 4 sequences we have a structure. And the red bits are beta strand. And the blue bits in the sequence, you see, are there any colored lines here? But I don't make it red in that sense, I'm lucky. Okay, anyway, so the blue bits are alpha helices in those 4 sequences, in the structures pertaining to those 4 sequences, and red is beta strand. Now, if you say, structure more conserved in sequence, I've already yelled out to you, then it's reasonable to say, look, if the alignment would be good, one way of looking at it and deciding about the quality is if are the red bits nicely aligned on top across and the blue and then red. And this is a so-called beta alpha structure. It is 5 times beta alpha. Beta alpha. The bottom sequence is the outlier. And where do you see the most shift? If you just look through your eyeball it a bit, look at and how well blocked is this? Here, already this guy is a bit too much to the right. You see that? But okay. Here, this the alpha helices. Not too bad, eh? Okay, let's give Crystal, it's on program. There's a nice guy. Here, let's say okay. Why not? And here it's sort of on top, but here we really get a little bit trouble, right? Because that should be there, and this should be there, and it's off. This is okay. Here, this is just complement for Crystal. That's great. Look at this. Huge gap in order to make this one fit pretty nicely. Well, then this one is off, but okay. In this region, right? This is good. This is what should happen. So, but if they should really be on top of one another, you can see that a 60,000 times cited program. So how many times do you think people ran it? 100 times more. Maybe this program is run 600 million times. I wouldn't be surprised. And this is sort of what you can expect in terms of quality. Are you happy? Do you think this is tricky business alignment, right? And okay, so I'm going to show this alignments a bit more, but I think I will do that the next time. Can I already? Yeah, I'm at the end. I'll show that next time. Yeah? But so one other thing. Last question for you. Am I allowed to ask it? No, but I'll do it anyway. You see these nice straight lines, right? Wow, biology. These sequences. Look, it's perfect. What do you think? Think about a block of 5 sequences and another block of 5 sequences. That's the last thing you do. You align those 2 blocks. What happens if you build up? If in the 5 sequences you decide to make a gap, what happens? Where is that gap? I don't think you're with me, so I'll try. That's really the last thing, I promise, okay? So we have a block of 5 sequences. Whatever is there, maybe there's a gap in it, I don't know. So these are 5 sequences, and here's another block with sequences in it. Now, as the last step in the progressive alignment, you align those 2 pre-aligned blocks. And we make the alignment like this. There will be a gap in that top block, and the other one will be under it like this. Suppose somehow here there were no gaps in that block. Where will the gaps be now? What will happen with the line here, necessarily? It will be nice and straight. Is that biology? Hopefully. Probably not. It is just the technique you use. Progressive alignment is doing this for you. And I've had so many happy biologists in my office. That helped make more. I'm so confident in my alignment because I see that gaps are placed so nicely and structured. And sometimes I didn't even wake them up. You have to place it. Okay, anyway. I'll leave it at this. Next time a bit more on the trickery to make things happen a bit more, okay? But so the figure is even a good program, I must say. The quality of multiple alignment is an issue. Yeah, that's